So we're going to look at what happens to a capacitor when I fill the gap in the plates with something else. So here are my plates. And I know that I have an electric field, so this will be some positive Q, some negative Q. I know that I'm going to have an electric field in the gap that looks like this. Okay, fair enough. Now, this of course is connected to a battery, and I suppose I should say I can disconnect this from the battery, and I will at some point, but let's leave this thing connected to the battery for now. So the battery in effect is holding the charges in place. This thing is charged, the battery is ensuring that it stays charged. Now what happens if I now fill this gap with another material? So there was just air here, but I'm going to take something and insert it. It could be wood, it could be rubber, it could be nylon or Teflon, something along those lines. Let's see what happens inside this particular substance, whatever substance it is. I shouldn't say particular, this substance in general. Remember, this substance is made up of atoms and molecules, right? We'll assume this is made up of atoms, and so there's my nucleus, and then I have this cloud of electrons outside of it. Fair enough. Well, I'm going to put this thing into an electric field that looks like this, which means there are positive charges over here, negative charges over here. And we know, of course, that the electrons are negatively charged. The nucleus is positively charged. So what happens? The electrons feel an attraction from over here, and the nucleus feels a repulsion from here and an attraction from here. And so once I apply this field, and we're going to assume that it's not strong enough to ionize anything. I'm not stripping off any electrons. I haven't applied that large of a field. I could, but I haven't. What this ends up looking like is this. Here's my nucleus. And now I've smeared out my cloud of electrons. And so my electrons are still everywhere, but what this means is that they spend more time over here than they do here. So in effect, I have polarized my atom, right? I've moved the positive charges over there, and I've moved the negative charges over here. And what happens, of course, when I do that, I get a small, very small, electric field that points in this direction from positive to negative. Right? Very, very small electric field. However, I've got trillions and trillions and trillions and trillions and trillions of atoms or molecules inside this substance. And so the effect here is cumulative. So if I put something in, I get an opposing electric field. It will not be strong enough to completely cancel the field. If it were a conductor, it would. This will not be strong enough to completely cancel the field, but it does lower the field. Okay. Well, if I lower the field, what does that mean for my charges? Remember, I could only put a certain amount of charges here because of the repulsion due to the same charges. But if I lower the field, what that enables me to do is actually put more charges on, right? These charges are going to want to be here now because there are a bunch of negative charges lining up over here that they are attracted to. So what that means, more charge appears on the capacitor. Hang on, let me close this door so we don't hear movies. So I put this substance in there, and then now I'm able to get more charge on the capacitor. I'm going to get a total charge of this Q plus some smaller, we'll say delta Q, right? Plus delta Q, right? So I'm going to get a little bit more charge that appears here. Now, how much more charge? Well, that depends on how this field works. What does that depend on? The substance. Different substances will produce different fields. Different substances show this effect differently. And in general, we're going to characterize that with a Greek kappa which is called the dielectric constant. The substance itself is called the dielectric, and this kappa is a way for us to characterize each substance. It's something you would look up on a chart, right? If you need a certain dielectric constant, you would go look, oh, what do I need? Oh, wax paper will work. I'll put that in there, which is actually a pretty good one. But the overall effect here is that I can now put more charge on my capacitor. Well, what does that mean? And I'm almost out of space here. Let me use this one, which is my my blank sheet here. So if capacitance is Q over V, all right, if I put more charge, V is still the same, I should point that out. V in this case is forced to be the same because the battery has not changed, right? The voltage that appears across the plates is going to be determined by the battery. I've got to have a voltage appear here that absolutely opposes this voltage. So whatever this voltage is, ultimately will be the voltage appearing across the plates. But what I can say now is that my voltage hasn't changed. My capacitance has, because if Q increases, the capacitance goes up, right? And so putting in a dielectric is actually a pretty good way to beef up the capacitance. And I can say this, that capacitance is equal to this kappa C naught, where this is the capacitance without the dielectric material, usually just called the dielectric. This is the capacitance of my capacitor. This is the dielectric constant of my material. This is my original capacitance. So if I put in a dielectric, I get a new capacitance. Notice if what I'm saying is that this capacitance is always bigger, that means the dielectric constant has to be bigger than 1, and it is for every material. But this is the general way I can determine the new capacitance if I insert a dielectric material into the gap.